Hi, welcome to Fertility Talks. I'm your host, Mary Wong, and I'm a Chinese medicine practitioner and acupuncturist, founder of Alive Holistic Health in Toronto, author of Pathways to Pregnancy, and your fertility coach. Tonight, I am so excited to talk about something completely different, and it's called CRISPR. And I have an amazing reproductive endocrinologist, Dr. Yaakov Bentov, here with us this evening, and we're going to discuss it in full detail. But before we do so, I just want to welcome you. Thank you for being here, and Yaakov, Dr. Bentov. And I'm just going to share with everyone who you are. First of all, you've already been on the show. And in fact, this is my live post number 111. And you did a post with me number 87 on metformin and fertility. And so we loved him so much. We wanted you back. I'm like, talk to me, give me anything. And so we're going to talk about CRISPR. Before I go on, I just mentioned that Dr. Bentov is practicing fertility and IVF since 2002, and initially at Soroka Medical Center, one of the largest fertility centers in Israel. He completed his medical degree, master's degree, OBGYN residency in Israel, and then finished his fellowship in REI, Reproductive Endocrinology and Infertility at UFT, University of Toronto. And he's currently holding a faculty position at the Department of OBGYN. Now, I know you're also an author to peer-reviewed research articles, and you're currently at ANOVA Fertility Center as a reproductive endocrinologist and the head researcher director there. And somehow you managed to have your own clinic at Juno, which is in Waterloo. And now you've just opened up another clinic in Guelph as well. Is that right?
It's true. Yeah, that's just week.
Wow. So that's really great. Absolutely. Because certainly in Guelph, that's a huge lacking. And I certainly see lots of patients that will come from all over just to come to Toronto, and much nicer to be able to travel less for those of you that are having fertility challenges, for sure.
We hope to make their lives a little bit easier.
Yeah, absolutely. And thank you for being here so that we can inform people that are going through fertility challenges, and again, making their lives a bit more hopeful, helpful, especially during this holiday season. So let's get on with it. What the heck is CRISPR, which is spelled CRISPR? What does it stand for?
So just the context. After we had our previous live Facebook event, you asked me, so what is the next big thing in reproductive medicine? And I immediately said CRISPR. And little did I know what's going to happen just before today's event, or last week, there was this big news about CRISPR and about the fact that in China, 2 twins were born, Lulu and Nana, which were the first babies to be modified by CRISPR.
That's right.
The whole world is now in turmoil about CRISPR because of this very unexpected development.
Yeah, so it's very timely that we're having this conversation, for sure.
So what is CRISPR? It's going to sound a little bit not related to fertility initially, but then I'll provide the context. So CRISPR stands for clustered. It's a long name. Clustered, regularly interrupted, short palindromic repeats. That's what CRISPR stands for, and basically, it's a phenomenon that was found at the late 90s by 3 different researchers independently. And they were examining microbes' DNA, and they found this very odd sequence of DNA where they had palindromic repeats. Palindrome is, like the famous Swedish band ABBA. You can, ABBA, you can read it from both directions the same way. So that's a palindrome. Right. So they found those palindromic repeats that had interruption by spacer DNA of different types. And they described it initially in Japan, Netherlands, and Spain. and not knowing what it meant or what it does. And later on, the Spanish researcher Mujica, his name, from Alicante in Spain, did some more research, and they found that him and another researcher from Netherlands, that those repeats are also associated with genes that often come as closer to those repeats, and they are genes which encode for enzymes that are involved with DNA repair, enzymes that fix broken DNA, which was interesting. Later on, they found, and again, 3 different researchers independently found that those spacer DNA sequences between those palindromic repeats were actually DNA that belonged to viruses, which was very interesting because it seems like the virus was trying to implant its DNA inside the microbes, the bacterial DNA, and the CRISPR was probably a mechanism to try and get rid of the DNA of the virus. It will not be transmitted to the other generations of bacteria. Oh, sorry, apologize.
So trying to fix the problem.
Yeah, no problem.
Yeah.
And therefore, that was implicated as part of the immune system of the bacteria. So that was the finding that was described in 2005. And later on, everybody was thinking about the potential of this enzyme, which can repair DNA. It could identify sections in the DNA and pull them out. So that's an editing tool. It can cut and paste defects in the DNA and fix them.
Right.
So of course that was very exciting, and people immediately started thinking about the immense potential of this editing system. And those 2 wonderful women in 2012, Jennifer Dudnay and Emmanuel Charpentier, they met in a conference in Puerto Rico, and they had a good time together, started a conversation about CRISPR, and they had this wonderful idea of why not create this modular enzyme that we can use to fix all kinds of problems in DNA so that we can solve all kinds of genetic problems. That was basically the beginning of this wonderful tool that became CRISPR that now we're all talking about. Pardon me.
Okay, so just so everybody knows, you are a diehard and you didn't cancel this interview because you're at the tail end of being sick. I had a person last week that canceled out on me because she was sick. So thank you for not canceling.
You're welcome. You're very welcome. So this CRISPR proved to be a very efficient tool for editing DNA. So what it does, as I mentioned before, it can cut and paste damaged DNA. Mm-hmm. For instance, if we carry a genetic disease, and there's many of them, like Huntington's or cystic fibrosis, where there's a mutation in the DNA, this enzyme can be designed to go into the cell, take the mutated part out, and insert a normal gene, or just take out the abnormal part of the gene, so that can fix the genetic disease and prevent its inheritance. So that was described as the most exciting scientific breakthrough for the year 2015. Those 2 researchers, sorry about that. Those 2 researchers are now candidates for a Nobel Prize, and hopefully that will be received soon.
Yeah.
So, of course, the potential was great to treat all kinds of problems. It's now actually being used to treat cancer by exposing cancer cells to CRISPR. CRISPR can change the way cancer cells behave. They can make them be more visible to the immune system so that the immune system can fight those cancer cells. So, and that's being used. Some of it is FDA approved. There's a lot of things going on all around the world, especially in China. China has been very liberal to the use of CRISPR right from the get-go. And there's currently more than 100 people in China that have been treated with CRISPR to fight all kinds of problems, including cancer, and in quite a good rate of success.
But are they not banning it for the use of fertility treatments though now in China?
So that was the big thing that everybody was worried about.
Yeah.
Using CRISPR on embryos. So if you treat cancer, so you treat the person, you treat the cancer cells, that stays with that person, that stays with those cells. But if you treat embryos, so that will be inherited, whatever you make from that point onwards. So initially when CRISPR, the whole notion of CRISPR came out, people were very anxious about the potentials of CRISPR and were very afraid to touch the subject. And it was banned by many, many countries. Mm-hmm. People slowly started warming up to it. Initially in China, as I mentioned, later on the UK, where especially in the UK, they were able to get the parliament to approve using CRISPR for research initially on embryos to check the action of certain genes in embryo development. So CRISPR allowed them to shut off certain genes and see what it does to embryo development. And the reason why everybody was so worried about CRISPR is because they all thought about not treating genetic diseases, but creating superhumans.
Right.
Better humans. Humans that can do things that other humans cannot by modifying their genetics. And then came Jiang Ku from Shenzhen University and materialized all the nightmares of everybody by creating those two babies, which are immune to AIDS. So they can never get AIDS.
Wow, I didn't know that.
He modified their genetics. So he basically created a superhuman in the sense that this is a human that cannot get AIDS.
Right.
And this is something we're all worried about because this will be essentially a GMO.
Yeah. Yeah.
So that would create this another class of people which their genetics have been modified to make them better in different ways.
Right.
And when I was reading for this conversation about CRISPR, I found a book, online book it's called CRISPR 101, which basically tells you exactly what you need to do, where you can get all those enzymes, how can you design the RNA that goes to these enzymes. So you can, basically the technology is out there. Essentially anybody can do it. And everybody's worried about the fact that people will start modifying embryos and creating humans which have capabilities and qualities which humans were not supposed to have, or at least evolution did not create humans with those qualities yet. So this is the context of what CRISPR is. Definitely, it's a big breakthrough in the sense that we can treat genetic diseases and prevent their inheritance. So, so far we can only screen. For instance, if someone, again, has Huntington's or cystic fibrosis, if a couple is a carrier or someone is a carrier of the disease, wants to have children, the only thing we could do so far is do PGD, where we would test the embryos and select the embryos without the mutation and put them back and create a pregnancy. However, if there's a problem of availability of the number of embryos to choose from, or if the mutation, there's many embryos which are affected by the mutation, sometimes there was not enough to choose from. So definitely CRISPR will provide a solution because you can fix those embryos and then put them back. And what this, I think is a physicist from China, was able to show that it's doable. It's doable in humans. It's pretty efficient. The indication that he did it for was not did not make any medical sense. He did it for couples where the husband was suffered from AIDS, was infected with AIDS, and the mother was not, to try and immune the babies from being affected with AIDS during the pregnancy, while everybody knows that it doesn't really happen. However, he did prove the concept that you can modify embryos, make them better. The CRISPR action is very efficient. It works. That was the proof of concept. It works. It works well, and you can create modified embryos and bring them to birth, to live birth.
So then, just to be clear, so would it be something like at the blastocyst stage, they would pull, biopsy some of the cells and then fix those cells and then inject it back? Is that what would happen?
That would fix only some of the cells. They do it at the
No, exactly.
It's only one cell, and what they do is basically inject the CRISPR protein, the enzyme CRISPR-9. It's called CRISPR-Cas9. The modified enzyme is called Cas9, and if you modify it, you can include in the enzyme DNA that will be able to essentially replace any part or add any section of DNA to your genome, but you have to do it at the zygote stage when the embryo is only a single cell.
Oh, right, of course, duh.
It starts to cleave. All the cells that will form in the embryo will contain the modified DNA.
Right, so it's before testing even. You're just doing it modified so that you're ensuring a good quality embryo. Okay.
So that all the cells will contain the same type of DNA.
Of course, yeah.
Then you can, as you mentioned, you can biopsy a few cells from the blastocyst to make sure you did a good job in creating the right composition of DNA that you wanted to achieve.
Crazy. Okay.
So
what could it? So do you foresee that it has a well? I mean, it certainly sounds like it has a huge role for IVF, but do you actually foresee it coming to fruition in the future?
So it's already happening. It's happening in China.
But they're trying to stop it, though, right?
I think there's a big backlash because of the fact that it was totally unexpected, and against all the common agreements and beliefs and consensus about what should and shouldn't be done. So that probably will throw everything back several years after people started warming up to the thought that it could be a good treatment and solution for couples with genetic diseases. And so definitely people will be very cautious with any relaxing legislation about CRISPR today more than they were 2 weeks ago.
Right, right.
But as I mentioned, technology is available. It's pretty simple. It's very effective. Anybody can do it. And what history taught us is that once a technology works and it's available, it will be used. So yes, probably it's going to happen, hopefully for the right reasons, and hopefully to solve problems and not try to fix humans and make them superhumans. We have a really bad history trying to make better humans. It's called eugenics, and people did it in all kinds of not so great ways before, with all kinds of race laws and trying to mate people with good genes with other mates with so history is not favored eugenics, and hopefully this would not be a tool for eugenics, but a tool to fix genetic problems. And in the right context, I think it's going to be an important addition to the things that we can do in reproductive medicine.
Absolutely. I just see it as a big heyday for all the lawyers involved for ethics, right? So the ethics committees will go crazy on this.
They are. And you just go on probably every news channel, every journal that was published in the past 2 weeks. Everybody relates to this CRISPR pandemonia, which was, again, totally unexpected. There's a movie that was made several years ago. It's called Gattaca, and the lead actor is Ethan Hawke.
Oh, no, I haven't seen it.
As to see it, but it's a sci-fi movie that talks about the world as it would develop into if CRISPR, not knowing about CRISPR back then, it's an old movie.
Right.
With GMOs, genetically modified humans, which became the norm, and all the ones that were what we call in research wild type, unmodified, were the outcasts. It's an interesting movie.
Wow.
And give us a reflection of what could happen if things go out of hand.
Well, what's interesting too, I know ideally it's more for people that already have conditions, genetic conditions, but now I'm thinking of, there'll be, how about the older population wanting to have a healthy embryo? Would that be utilized for that as well?
Well, we don't know of genes that are in charge of aneuploidy. Hopefully we would someday.
Yeah.
Today we know just about the correlation of an abnormal number of chromosomes and age. Nobody really knows too much about the mechanism. We know that some of it is programmed, some of it is probably secondary to damage caused by free oxygen radicals, or something you probably know a lot about. But nobody knows about specific genes, and CRISPR can fix genes. It cannot fix an abnormal number of chromosomes. Well, today, at least today. So maybe in the future it might. It's mostly meant to fix genetic problems, single gene mutations.
Right. Right.
And
very exciting.
It is exciting. And and hopefully things will go back to the place where they're supposed to be. Not creating superhumans, but rather fixing genetic diseases, preventing inheritance of crippling medical conditions, which CRISPR provides a wonderful promise.
So then, you keep on saying, oh, anyone can do it. Well, any embryologist or people in the lab, sure. But so having that tool, then are you saying, well, I know China is utilizing it, but are there any Americans or Canadians looking to start utilizing it?
So it's being used, as I mentioned, FDA approved CRISPR to treat cancer. So it's being used not on embryos.
Got it.
To treat conditions on humans, on parts of their cells, not on embryos. So what is currently being practiced could not be inherited to future generations. This guy, the Chinese researcher, he deleted the gene that is the backdoor for the AIDS virus. So it cannot enter the cells because this gene now is missing. Nobody knows what other implications might be to the fact that this gene is missing.
Right.
So nobody knows anything about it. Nobody knows what's going to happen in the future of those babies because of the fact that he took a gene that HIV virus uses to get into the cells, but it might have other important functions in the body.
Absolutely. Yeah.
And from now onwards to all generations that will be formed from those babies, this gene will be missing. So nobody knows what that's going to cause. So it's a big mystery, and you have to think about the fact that every change that you make will be inherited onwards to the future generations. It could be hundreds and thousands of people formed from these modified genetics. And you have to be responsible and think about that. So as I mentioned, right now, only people are being treated on parts of their bodies in America and probably Europe. But China, unless it makes, as a reaction to what happened, changes in the legislation, still allows treatment of embryos.
Crazy. Well, that is a very exciting topic, and one that we will see more and more of, I am sure, as this already made headway a couple of weeks ago, as you mentioned. Yeah. So thank you for that. Is there any other insight that you want to provide for our viewers with regards to this?
Well, it's a CRISPR is a really strong research tool, and as a research tool, it allows us to study genes and the action of genes. People made all kinds of modifications to CRISPR to allow systematic disactivation or downregulation of genes, so that you can see, if you chop or inactivate certain genes, what it does to the phenotype. So that's a wonderful way to learn about what genes do and what their products are important for. One example, for instance, we know that there is bacteria that develop resistance to antibiotics, and we often do not know which of the genes in those bacteria creates the resistance to the antibiotics. So what you can do today with CRISPR, you can take several samples of those bacteria and systematically turn off their genes and expose them to the antibiotics and see what gene inactivation allows the antibiotic to kill the bacteria. So you would know exactly what provides the bacteria with the ability to resist the antibiotic. So that's a wonderful, very, very strong, very effective research tool, other than clinical treatment.
Well, that would be great, because of course there's so many strains that are completely antibiotic resistant. I mean, that's where you have the super bacteria and viruses now. People are staying sick longer. So hopefully that'll change for the future as well.
Absolutely. And hopefully we'll not see too many superhumans as well.
No. Another sci-fi movie coming out, sure.
Shortly.
Yeah. So for those that have just joined in, we were talking about CRISPR, and so please go back. This will be replayed. I know it's live right now, so please check it back out after. And otherwise, also live post number 87, Dr. Bentov and I were talking about metformin and fertility. Next Wednesday, do you hear a static? Are you okay?
Nope. No.
Oh, okay, it's weird. There was major static on this end. Okay, so next Wednesday, 8:30 p.m. Eastern Standard Time, I'll be talking to one of my former patients who is currently pregnant and was told that she would never be able to carry a baby because she had Asherman's, which is basically severe scarring of her uterine lining, in which they basically said she could not carry a baby. She would have to use a surrogate and a gestational carrier. And the other thing was that when she was coming to see me, she wasn't even having regular periods at all. So it was amazing to have her transform, and I'll let her tell you her miraculous story. So that's next Wednesday, 8:30 p.m. Eastern Standard Time. And I just want to add in, because it is holiday season, I know for a lot of you out there who are having fertility challenges, this is a very difficult time of year, because it's a festive time of year. And although many people are happy and running around shopping and having family gatherings, it's a difficult time, because it's also a sad time, because all you want is a baby in your belly. So what I want to add to is there's Erin McCullough started this group, and it's called Secret Snowflake Holiday Support. And I really invite you to join this group. I have nothing to do with it. I'm just saying it because I checked it out, and it's one of the few, or actually I'll tell you right now, it's probably the only one I've seen out there that is really a positive place. I find there's a lot of chat groups and stuff. I call it blind leading the blind, and it gets you down this bad rabbit hole. And this group is actually very positive. So check it out, get supported during this holiday season. And I hope to see you next Wednesday. And if you haven't picked up my book, please do so, Pathways to Pregnancy, for some good hope and good reading for this holiday. So I'll see you all next Wednesday, 8:30 p.m. Eastern Standard Time. Thank you, Dr. Bentov, again for joining me. And we have just prior discussed about we need to have you back, and your wife, who she's an embryologist, right? Is that right? Or
she's a reproductive biologist.
Okay.
She does research on reproduction.
Perfect. Well, And the two of you have been doing some research, and this is with regarding PCOS, polycystic ovarian syndrome. And so that sounds like a great topic to go into, and we'll look forward to having that discussion in March.
Thank you very much, and congratulations to your patient.
Oh, thank you. Yeah, you'll have to watch it. And you stay tuned. Bye, everyone. Have a great night. Okay, take care. Mwah.